Welcome to a new lesson. In this lesson, we'll be using quadratics to link graphs, numeric, and algebraic formats. Let's take a look at our first example. In this example, we have a parabola on the right-hand side, and we are asked to find the equation of this quadratic. Well, there are two ways to find the equation of this quadratic. The first way, using the vertex form. The vertex form is used if we know the exact location of the vertex, like here. As you can see from the graph, it's really hard to find the vertex point. Because it is difficult to find what the vertex point is, vertex form doesn't really work for this parabola. However, there is a different way to find the equation of this parabola, and that is using the factored form. The way that the factor form works is that it deals with the a value as well as the x-intercepts. And from the graph, you could actually see the x-intercept quite clearly. One of the x-intercept is -4. The other one is -1. And the way that we will solve this equation is that we're actually going to be solving just for the a value. And we're going to take these, the x-intercepts, and a point on this graph, like for example this point, the y-intercept, which would be 0 and +6. And we're going to put these values into our equation and solve for a value. Now, once we solve the a value, then we could find the equation of our quadratic. So it's a little bit tricky at first, but once you do a couple of these problems, then I'm sure you get a hang of it. So let's take a look, and let's solve for our a value. So we know that our x value is 0, our y value is 6. We know that well, our x-intercepts would be -4, so that would be our r value, and the s value for our x-intercept would be -1. So we're going to put all those values into our equation, and we're going to solve for our a value. So now our y value is 6. We're looking for a. We don't know what that is. X is 0 minus -4 for our r value. Our x value, again, would be 0. And that would be minus -1 for our s value. And then let's take a look at what happens inside the brackets. So we have a, 0 minus -4 is just 4. 0 minus -1 is just 1. And then we'll get 6 is equal to 4 times 1 is 4, so we got 4a. Then we divide both sides by 4, and we get 6/4 is equal to a. And then if we reduce, we get 3/2. So now since we've solved for a, we just have to plug a back into our original equation, where y is equal to 3/2. And then we'll just put in the r value and the s value into our x-intercepts. So the trick is also, because the x value, if the x-intercept is -4, we can just flip the signs if it's negative, and here we go. And that's how we get our equation of the parabola. A little bit tricky, but I'm sure you can get better at it as time goes on and you practice a little more. In this example, we're going to recall how to draw a quadratic in a vertex form. So let's recall our steps. So our step were 1, 2, 3, or actually 1, 3, 5. And the first thing we have to do is we have to multiply this by the a value, which is -2. And we get different steps. So we have 1 times -2 is -2, 3 times -2 is -6, 5 times -2 is -10. So our steps are -2, -6, and -10. The other thing we have to recall is that we first have to start with the vertex. So our vertex is depicted from our vertex form, and our vertex form will have a vertex of -1 and 1. So remember that wherever we have in the bracket, we switch the signs of our x value for the vertex. So because it's -1, it becomes +1, and just recopy the +1 outside the bracket for our to finish our coordinates of the vertex. So that's the first thing we'll do. We have to start at that point at 1 and 1. So if you go to the graph, 1 and 1 is about here. And then we're going to use our step values. So the step values says that we first have to go 2 units down and 1 unit across. So we'll have to go, usually I like to go across first and then 2 units down because of this 2 negative. And then next thing is of this -6, so that means for the 1 unit across, we'll go 6 units down. 1, 2, 3, 4, 5, 6. Now, I don't have enough space on this graph to do my next step, which is -10, so I'm just not going to do it. And this should be sufficient enough to draw this parabola. So now I'm going to draw dotted our axis of symmetry, and I'm just going to do the same thing on the left hand side as I did on the right. So again, I'm going to go 1 unit to the left and 2 units down, and 1 unit to the left and 6 units down. 1, 2, 3, 4, 5, 6. And now what I'm going to do is use a different color, and I'm going to connect these points in a way that it looks like a parabola. Don't forget about the arrows, and do your best to connect the lines. And here we go. This is how you draw a parabola in a vertex form. In our next example, we're going to prove that these dots that sort of look like a parabola actually create a parabola. So the way we're going to do it, we're going to use it with a table of values. We're going to create a table of values just by looking at the coordinates of each and every point. So if you look at these coordinates of each and every point, this is the following table of values you should get. And here we go. So these are all the coordinate points for our so-called parabola, if we imagine it. So by looking at the table of values, you can't really see if this is a parabola or not. But we can use the table of values to find our first and second difference. And if our second difference is a constant value that's always repeating, then we know that it's actually this is actually a quadratic equation. So let's take a look at our first differences and our second differences. Now it doesn't matter which way you subtract the 0.5 from 3 or from 3.5 as long as it's consistent. I like to use positive values, so I'm going to subtract the small one from the bigger one. So I'm going to actually subtract 3 minus 0.5, and I'm going to get a second difference of 2.5 this way. Then I'll subtract 4.5 minus 3, and I get 1.5. Then 5 minus 4.5 is 0.5. And if I continue on this pattern, these are the differences that I'm going to get. So the first differences don't really matter for us. If the first difference was the same number, then this would be a linear or a straight line relationship. So what I'm interested in a second difference. So now I'm going to subtract 1.5 or 2.5 from 1.5. Notice what happens. You get 1. How about 1.5 and 0.5? You get another one. And then 0.5 minus negative 0.5, you get another one. Oh, we get another one. Oh, we get another one. So notice the second difference is consistent, and it's because of this consistency, or a constant value, that shows us that indeed, so therefore, this is quadratic function, parabola, what have you. In our last example, we'll take a look at a known parabola that's given to us by this table of values, and we're going to be trying to find this equation. And what's interesting about this is that we don't know really the x values, sorry, not the x values, but the x-intercepts in this equation. We know one. No, we don't know a single one. And how do we know that? Is because normally with the x-intercept, we would have a value of 0 for the y, and then some value for the x, but we don't know that. Because of this, we can't really use the factored form. You probably recall from the first example, this is your factored form. It only works if we know the x-intercepts, but we really don't know those x-intercepts. But looking at the table, we could maybe even find the vertex. And the way we find the vertex is we look at the symmetry in the table, and we specifically look at the y values. So we're basically looking for the maximum minimum value. And look at the negative 11s and look at the negative 5s. So now we have the 11s, negative 11s, negative 5s, they're symmetrical. So usually what happens, because of the symmetry, the highest or the lowest value for the y, in this case it's negative 3, turns into our vertex. So actually we have the vertex. So vertex would be negative 1 and negative 3. And what form of the quadratic formula has the vertex? And that's the vertex form. Here you go. This is the vertex form, and right away we know our h value. Well, our h value would probably has something to do with the negative 1, and our k value would probably be just negative 3. The other thing that we're missing from this piece is that we're missing the x and the y value. And the x and y value would be any other point besides the vertex from this table. So the easiest one would probably be deal with. It would be the 0 and the negative 5. This would be our x value. This would be our y value when we plug it in. And again, we are looking for the a value like the first example, except now we're dealing with the vertex form instead of the factored form. So let's plug those values in, and again, solve for the a, and then state the final answer with the known a values and the vertex values. Okay. So the y value that we picked was negative 5. The a value we're trying to find out. X value would be 0. The h would always be the opposite of this one. So that would be positive 1 squared. And the k value would be negative 3. And now we're just solving for the a value. So we have negative 5 on the left-hand side. We have a times 1 to the power of 2, that's just 1, minus 3, and we just use reverse BEDMAS. We add 3 to both sides, or we just move the 3 over like that, change the sign. We have just a times 1, which is just a, and we have a negative 5 plus 3 is negative 2, and that is equal to a. So our a value is negative 2, and now we just rewrite the equation so that we have the a value, negative 2, and include the vertex, which is positive 1. Remember, always the opposite of the x value for the vertex, and minus 3. So this is our equation of our quadratic based on the table of values that was given.